Hello students, welcome back to the series Coordination Chemistry. In this module, we are dealing with the last part of theories of coordination compounds. Here, we are dealing mainly with the last two theories, that is ligand field theory and molecular orbital theory. And before that, we have to discuss about some of the merits and demerits of crystal field theory. That is a just previous theory, that is crystal field theory. What are the merits and demerits? Number one is it could give a fairly good explanation for the geometry of complexes. That is, we have studied different geometry of complexes, tetrahedral, square planar, octahedral, etc. And all these complexes, the geometry could be very well explained by this crystal field theory. And the second one is when we are considering the four coordinated complexes, it could it could distinguish two types of four coordinated complexes, that is tetrahedral and a square planar. Whether a complex forms a tetrahedral geometry or whether it forms a square planar geometry, those distinguish, that is that type of distinction between the four coordinated complexes could be given by the crystal field theory. And also it could explain the inner and outer orbital complexes in valence bond theory. We have discussed about the valence bond theory and what are inner and outer orbital complexes. That distinction could be given by crystal field theory also. And another merit is that it could explain the magnetic properties of complexes. The complexes shows different magnetic properties depending upon the type, depending upon the number of electrons present in the d orbital, and that could be explained by this crystal field theory. And it could also explain the spectral properties of the complexes. Spectral property means color, about what is the color and how the complex shows the color. Everything could be easily explained by the crystal field theory, and these are the merits of crystal field theory. And moving to the demerits, although it has many merits, demerits were also there for the crystal field theory. And number one is that since crystal field theory is mainly discussing about an electrostatic interaction between the metal and the ligand. So, in that case, electrostatic interaction means the crystal field theory considers a metal ligand bond as an ionic character. It is the ionic character of metal ligand bond is mainly considered by the crystal field theory. But the problem is that it doesn't give any importance for a covalency. So, it was found that some kind of covalent character is there in the metal ligand bond. So, according to crystal field theory, no consideration was given for the covalent character or covalency. That was the first demerit. And now it fails to explain the relative strength of the ligand also. Since we have studied different weak field and strong field ligands, two types of ligands are there based on their ability to split the d orbitals, and but this crystal field theory could not give any explanation regarding the relative strength of this field, whether it is how far it is strong or how far it is weak. That type of relative strength of the ligands was not at all explained by the crystal field theory. And another demerit is that the chemical properties and bond strength, that is the chemical properties of the complexes and the strength of the bond, it cannot be explained without considering the covalency. It was found that with the help of covalency only we can actually explain the bond strength and the different chemical properties of these complexes. Since the crystal field theory is not considering covalency at all, this is the main demerit as far as the CFT is concerned. And now the last is that the charge transfer between the metal and ligand could not be explained by the crystal field theory. Then what is actually charge transfer? Actually, in the this coordination complexes, they show color, and the formation or the color is mainly due to the DD transition, that is ligand field spectra. But some complexes which are not having any DD transitions still shows color, and it was mainly due to the charge transfer. Charge transfer means the electron transfer from the metal to ligand or the ligand to metal. So, that is metal to ligand and ligand to metal electron transfer, and with this transfer the complexes shows color. But this crystal field theory was mainly concerned with only DD transition. So, when charge transfer transitions are there, it was not it failed, CFT failed to explain those kind of transitions. So, these are the demerits of crystal field theory. And now the modern theories came after the crystal field theory, that is adjusted crystal field theory. Now, we have the adjusted crystal field theory, or it is ligand field theory, and all the outcomes of crystal field theory are considered here. All the positive outcomes of crystal field theory are included in the ligand field theory, but the difference is that the metal ligand interactions are not considered purely electrostatic in the ligand field theory. That is, some kind of covalency is considered in the ligand field theory. That was the advantage, or that is why it is called as adjusted crystal field theory. That is, all the outcomes were considered from the crystal field theory, but additionally covalency was included in the ligand field theory. And how can we say that there is a kind of covalency in a molecule? The evidences was given by we have some of the evidences that shows there is considerable covalent character in the metal ligand bond, and these are the evidences. Number one is nephloxitic effect. And what is nephloxitic effect? Before that, I have to say that we have d orbitals and we have d electrons, that is electrons which are occupied in the d orbitals. In the metal, the d orbital, d electrons will be having a kind of repulsion. When the electrons are there, filled there will be a kind of repulsion, and that is the interelectronic repulsion, between the electrons, that is called as interelectronic repulsion. And in the metal, if there is a repulsion, there will be a parameter showing the interelectronic repulsion. It is called as interelectronic repulsion parameter. It is represented as capital A, B and C, or it can be called as Recche parameter. So, interelectronic repulsion parameter is called as Recche parameter, represented as capital A, B and C. It is present in all metal complexes or complexes as well as a free metal ion, and when it was investigated, it was found that the Recche parameter or interelectronic repulsion parameter is very much less when a metal is complexed with the ligand when compared to the free metal ion. That is, the free metal ion experiences greater interelectronic repulsion when compared to the complex. So, the value of Recche parameters is less than the complexes than the metal ion. When free metal ion is considered, there will be obviously there are d electrons, and the interelectronic repulsion in the free metal ion will be greater when that metal ion is complexed with ligand or in complexes. And upon complexation, this metal orbitals, they expand. See, the metal orbitals, d orbitals are having a particular shape, that is everything is discussed earlier, and the metal d orbitals will be having a particular shape with the electrons inside that. And when in the absence of any complexation, or if the metal ion is in a free state, that metal orbitals will be oriented in a particular direction, and with that there will be a interelectronic repulsion. Upon complexation, what happens? This metal d orbitals will be expanding. Why it is expanding? For a better overlap with the ligand orbitals. See, metal orbitals and ligand orbitals should overlap, right? And then only metal ligand bond will be formed. And for the effective overlap, this metal d orbitals will be expanding, and that is called as d cloud expansion. Metal or d orbital expansion is also called as d cloud expansion. And it was found that since the d cloud expansion is present, which means that there will be a covalency, because the d orbitals are expanding. Why are they are expanding? For the effective overlap with the ligand orbitals. So, the extension of d orbitals occurs to maximize the overlap of ligand and metal orbitals. And the greater the decrease in interelectronic repulsion means there will be a greater covalency. Since there are the metal d orbitals with the electrons are there, interelectronic repulsion is there. To decrease the interelectronic repulsion, what happens? These d orbitals expand to complex or to overlap with the ligand orbitals. In that case, what happens? The interelectronic repulsion decreases. That is why I have already told that in the case of a complex, the interelectronic repulsion is less when compared to the free metal ion. And when there is a greater decrease in interelectronic repulsion, you can say that covalency is greater or covalent character is greater in that case. And we have the nephloxitic ratio, that is represented as beta. Beta is equal to B dash by B. Then what is B? A, B and C are the Rache parameter or interelectronic repulsion parameter. B dash is the interelectronic repulsion of the free metal ion. B dash is the interelectronic repulsion of the complex and B is the interelectronic repulsion of the free metal ion. Since beta is equal to B dash by B, which means that B dash is the interelectronic repulsion of the complex divided by interelectronic repulsion of the free metal ion. And we have already studied that the interelectronic repulsion is greater in the free metal ion when compared to the complex. So, you have the numerator higher than the denominator higher than the numerator. The numerator is less, denominator is more, which means that beta is always less than 1. Why beta is always less than 1? B dash is less than B. Always it is like that. And now that is all about the nephloxitic ratio or nephloxitic effect. What is the nephloxitic effect? It is a d cloud expansion. D cloud expansion shows an evidence for the covalent character of metal ligand bond. And now we have the second evidence, that is intensity of electronic transition. See, I have told that the color of the complex is mainly due to DD transition, means the electronic transition between the d orbitals from one d orbital to another d orbital. It is called as DD transition or it is ligand field spectra. In the complexes which are not showing DD transition or which are not capable of DD transition are still showing colors. That is, they may be having a high intensity colors, and that color, the occurrence of that colors was attributed to the charge transfer transition. So, some transitions which are highly intense, which may be due to the charge transfer. Charge transfer means what? The transfer, the electronic transfer from the metal to ligand or from the ligand to metal, means that there is a kind of covalency in the complex. So, this charge transfer transitions are also an evidence for the covalency. And the third one is ESR spectra, electron paramagnetic spectra or electron spin resonance. ESR or EPR, electron paramagnetic resonance spectra, or ESR spectra means electron spin resonance spectra. In that case, this ESR spectra is mainly shown by the unpaired, the complex is showing unpaired electrons. In ESR spectra, we have the hyperfine splitting. Hyperfine splitting occurs only if there is some kind of delocalization. Delocalization means what? There is a covalency. So, hyperfine splitting is also an evidence for the covalency. And now, fourth evidence is NMR spectra. NMR spectra complexes also shows that some kind of covalency is there in the metal ligand bond. And we have the evidence from NQR spectra. This NQR spectra also shows there is some kind of covalent character. And finally, we have the Landé splitting factor or G factor. G factor is it is there in the G factor for the electron is free electron is 2.003. This G factor is also an evidence for the covalent character. And so we can say that the metal ligand bond is having considerable covalent character. That is the occurrence or the emergence of a new modern theory, that is a adjusted crystal field theory or ligand field theory. And finally, we are moving to the most modern theory, that is MO theory. Here also we are considering that the metal ligand bond is having considerable covalent character. Not at all there is a complete ionic character was ruled out in the most modern theories. And now what is molecular orbital theory? The most important theory and the most advanced theory in coordination compounds. You have studied in your lower classes about MO theory of molecules, simple molecules. And what was the basis of MO theory? MO theory, molecular orbitals, MO theory was concerned with the combination of atomic orbitals to form the molecular orbital. So, the main point is that atomic orbitals will be combining to form the molecular orbitals. Number of atomic orbitals combining will be equal to the molecular orbitals formed. That is the main concept there. And if we are discussing about coordination compounds, we are considering the molecular orbitals which are formed by the metal and ligand to form the molecular orbital MO orbitals. So, these are the salient features of MO theory. First one is, number one, obviously it is the molecular orbitals are formed by the combination of atomic orbitals. So, the combination of atomic orbitals means which are the atoms or which are the components involved here. We have the central metal atom. We are discussing about coordination compounds, we have central metal atom and ligands. So, we have to consider the atomic orbitals of the central metal atom and ligands. And now we have the combination of atomic orbitals of central metal ion and ligands occurs when they, what are the conditions for the overlap of atomic orbitals of this metal ion, central metal ion and the ligands. They combine when conditions of energy, overlap and symmetry permit. When the conditions of energy, overlap and symmetry permit. And when these conditions are matched, these atomic orbitals will be combining to form the molecular orbitals. And now the metal d orbitals and ligand group orbitals will combine to form molecular orbitals. We know that in the case of coordination compounds there is a central metal ion. So, central metal ion is having atomic orbitals there. In the case of ligands, ligands will be collectively called as ligand group orbitals, LGOs, ligand group orbitals. So, these LGOs will be combining with the metal orbitals to form the molecular orbitals. And the metal atomic orbitals that are involved in the combinations are 3d, 4s and 4p. 3d means it is a d electrons, 4s s orbital and 4p means p orbital. So, 3d, 4s and 4p are involved in the combination if we are discussing about metal orbitals. And the ligand orbitals which we LGOs are sp3 hybridized orbitals, that is one s orbital and 3 p orbitals combined to form sp3 hybridized orbitals. If we are discussing about the sigma bonded complexes, means metal ligand bond is sigma, it is not at all pi, only sigma bonded complexes are considered here. So, the metal atomic orbitals overlap with the ligands based on the symmetry. Then this it was obtained from the principles of group theory, how the symmetries are matched. We know that there is an s orbital. So, s orbital is having the symmetry A1G, it is designated as A1G. P orbital is designated as T1U. EG is, we have two type, that is d orbital we have EG and T2G, and EG we know that it is dz square and dx square minus y square. T2G means we have 3 dxy, dxz and dyz. So, these are the symmetry. and the same symbol is given with capital letters for the molecular orbital. We know that the atomic orbitals of metal and ligand group orbitals combine to form the molecular orbitals, and the designation of molecular orbitals is simply as the above, but we are giving capital letters, that is A1G, A is capital, T1U, T is capital, E, EG, E is capital, and T2G, T is capital. So, that and this is the way we have to distinguish among the atomic orbitals and molecular orbitals. See, we can consider the complex CONH3 6 times 3 plus. This complex has a central metal atom cobalt with the ligands ammonia. Ammonia, how many ammonia ligands are there? We have 6 ammonia ligands. And now, while calculating the oxidation state of the central metal atom cobalt, CO3 plus, because ammonia is having 0 charge. So, CO3 plus means it has D6 configuration, that is 3D6 configuration, 6 electrons in the d orbitals, that is with the central metal atom. Now, ligands, how many ligands are there? We have 6 ammonia ligands, each ligand is giving 2 electrons to the central metal atom. And totally how many electrons are being donated by the ligands? 6 into 2, that is 12. So, on total how many electrons are there with the central metal atom? It is 12 plus 6, 12 plus 6, that is 18. Okay. So, total we have 18 electron for the system, and as far as we have discussed about the molecular orbital salient features, this is the way they are combining. You can see in the left hand side it is metal orbitals involved, and the right hand side you have ligand group orbitals. Ligand group means what? Which are the ligands? They are ammonia ligands. So, ligand group ammonia orbitals are there in the right hand side. Left hand side you have metal orbitals. How many? Which are all the metal orbitals involved? That is 3D, 4s and 4p. 3D means you can see the 3D, 5 3D orbitals. S, 4s means S we have only one orbital, that is here. This 4p means we have 3 p orbitals, px, py and pz. The designation is like this: S is having A1G, p is having the symmetry T1U, and d orbitals Eg and T2G. Okay. And now, what is MO theory? It is a combination of atomic orbitals to form the molecular orbital. So, metal atomic orbitals will be combining with the ligand group orbitals to form the molecular orbital. So, simple combination means it cannot combine in different ways, only with the symmetry, when the symmetry energy etc. should the condition is that a symmetry energy etc. should be matched. See this. The d orbitals, we have 5 d orbitals. 5 d orbitals means we have 2 sets, that T2G and EG. This T2G orbitals remain as the non-bonding, that is we are not considering the pi interactions. So, this T2G orbitals are involved only in the pi interactions or pi bonding. So, they will be remained as such, and rest we have 2, that is EG orbitals. So, we have the EG and EG star. EG means the bonding, EG star means the anti-bonding. In the case of when we are considering the s orbital, that is A1G, A1G of the metal will be combining with the A1G in the ligand group orbital to form two atomic orbitals combine to form 2 molecular orbital. So, A1G and A1G star, one bonding and one anti-bonding will be formed. We know that the bonding and anti-bonding molecular orbitals are formed by the positive combinations, and the anti-bonding molecular orbitals are formed by the negative combinations. So, one bonding and one anti-bonding is formed by the combination of A1G of the metal with the A1G of the ligand. So, A1G and A1G star. A1G is having the lowest energy. And now considering the T1U of the metal combining with the T1U of the ligand group orbital. T1U means we have 3 T1U. T1U when combined with the T1U of a ligand group orbital in the positive combination, you have the bonding molecular orbital, that is T1U. It is all the molecular orbitals should be represented in the capital letters. So, T1U bonding, and in the top you can see T1U star, that is the antibonding. Star is denoting the antibody, that is already studied in the MO theory in the lower classes. You may be knowing about this concept. So, bonding and antibonding molecular orbital. Bonding molecular orbitals are formed by the positive combination, antibonding molecular orbitals are formed by the negative combination, and this T2G remains as such because they are not involved in the, so they are meant for pi bonding, and this is the way of forming. And another thing that should be kept in mind is that while the formation of bonding and antibonding molecular orbitals, the bonding molecular orbitals are having more ligand character and anti-bonding molecular orbitals are having more metal character. That is why it is some kind of, it is drawn as a slanting, in a slanting position, because these orbitals are more to the ligand side and these orbitals are more to the metal side. So, bonding are having more character of ligand character and anti-bonding are having more metal character. That is the way. And we have calculated number of electrons in the complex. How many electrons? We have calculated that it is 18 electrons. And how to fill the 18 electrons? See this again, Hund's rule of maximum multiplicity, Aufbau principle, etc. should be followed here also. So, each orbital will be having 2 electrons maximum. So, in the lower one T1, it is T1 A1G. It is having the lowest energy, that is it will be having 2 electrons. So, A1G 2, T1U, how many T1U? It is 3 T1U. So, 1, 2, 3, 4, 5, 6, 7, 8. EG will be, there will be 2 bonding EG orbitals. So, 8, 9, 10, 11, 12 and rest 6, 12 plus 6, that is 18. Rest 6 should be occupied in the T2G orbital. They are remaining as the non-bonding there. And here also you can see the crystal field splitting is also there, that is represented like the delta O. It is shown here, that is the energy difference between T2G and EG. So, that energy gap is delta O. And when we observe the complex, you can see that there are no unpaired electrons in the complex. Unpaired electrons, no absence of the unpaired electrons means the complex is diamagnetic. So, the magnetic behavior of the complex is diamagnetic, and this is the way to fill the electrons. Again I can explain how the metal molecular orbitals are formed. We have metal 6 sigma orbitals. Metal 6 sigma orbitals are 1s, 3p and 2eg. So, s we have 1, p we have 3. So, 3 plus 1 4, 4 plus 2, eg means we have 2 orbitals. So, 4 plus 2 6, that is why 6 sigma orbitals are there in the metal. And this 6 sigma orbitals should combine with the ligand group orbitals. So, 6 LGOs that has symmetries that match the metal orbitals are, that is ligand group orbitals should have their symmetry which are matched with the metal orbital, that are s, p and dz square, dx square minus y square. These are the ligand group orbitals having the same symmetry with that of the metal orbital, and that is why these both of them are combining. And now the rest we have 3 T2G orbitals, they are not suitable for pi bonding, that is why they remain as such. And now we have studied how to construct the molecular orbital diagram of a complex. Qualitative MO diagram was constructed taking cobalt CONH3 6 times 3 plus as an example. The main thing in molecular orbital theory is that the molecular orbitals are formed by the combinations of atomic orbitals, and which are the atomic orbitals involved? We have the metal atomic orbitals and the ligand group orbitals. That is the difference in the coordination compounds. Usually when we discuss about the MO theory of simple complexes, you have only you have separate atomic orbitals for each atom, but in the case you have in this coordination compounds we have ligand group orbitals or LGO. O's. They will be combining according to the symmetry, energy, etc. When these match, they will combine effectively to form the molecular orbitals, and different molecular orbitals are formed. Electrons are being filled in the molecular orbitals according to the Aufbau principle, Hund's rule of maximum multiplicity, Pauli's exclusion principle, etc. These are the things in the molecular orbital theory. And in this class we have discussed about the advanced theories that are crystal field theory was the one of the newest theory, but some of the drawbacks are there for the crystal field theory. The main thing was crystal field theory considers the metal ligand bond as a purely ionic one. Changing that concept, we are introducing a covalency into the modern theories, and so modern theories like ligand field theory and molecular orbital theory came into existence, and they were effectively discussing about the covalency in complexes. So, in the next module we will be discussing about the spectral and magnetic properties of these complexes. In that we will be discussing about various complexes, magnetic properties of complexes such as paramagnetic, diamagnetic, how the complexes shows colors, etc. Thank you all for watching now. Thank you.